S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
So in the first part of chemical kinetics, we have discussed about the differential and integrated forms of rate of reactions, rate law expressions, and we've also talked about the order of a reaction. Now in this particular presentation, I am going to continue with the methods to determine the order of a reaction, like how can we measure the order of this reaction, of any given reaction experimentally. Welcome to S. Chan Academy, myself Dr. Mamta Sethi. So today I will be discussing with you various methods to determine the order of a reaction and various theories of reaction kinetics. To read more about this topic, please refer to the book by S. Chan Publishing. The link to the ebook is given in the description box. So in the earlier presentation, we had discussed about the order of reaction. In this particular presentation, I am going to discuss various methods to find out the order of a reaction experimentally. First of these methods is use of differential equations. Now we have already understood the concept of differential form of rate law, right? So according to differential equation, differential form of the rate law, rate is given by, rate I can denote it by small r also, is given by K n C, which represents the concentration of the reactant. So R here is the rate of a reaction, Kn is the rate constant for nth order reaction, C is the concentration of the reactant, and N is the order of reaction. So what is our unknown over here? It is the N. We want to determine order of a reaction. So how can we determine the order of reaction? It is quite simple. If we take log of this particular expression, it then becomes log of R. Of course, I am talking about natural log, log of Kn and N log C. Now this is a kind of equation which we can correlate with the equation of a straight line. And if I plot a graph, so between log of R and log of concentration. So what can I do? I can plot the double logarithmic graph, right, in this way, where on y-axis I will have log of rate and on x-axis I have log of concentration, and this is going to be, as per this equation, a straight line, an increasing straight line, the slope of which, so this can be compared as y, and this is your mx and this is c. So y is equals to mx plus c. So according to this plot, the slope of this plot will give me n. That is the value of the order of the reaction. So alternatively, we can do one thing, that we can determine the rate of a reaction for a particular concentration. We can call it a rate 1. So alternatively, we can use this differential form of the rate law expression in order to find out the order of a reaction. What do? We can find out the rate of a reaction at a at a fixed temperature for a fixed concentration, which is C1, and for another concentration, which is C2, we can then take the ratios. Rate constant for a specific reaction will always remain same. So therefore the ratio of the rates will be equal to rate 1 upon 2 is equal to C1 upon C2 raised to the power n. Now we can see that easily. If I know the rate of a reaction at concentration C1, rate of the reaction for concentration C2, 2 I know, then I can find out the n. So n is the only variable. I know all these quantities, so n can be calculated. This is one method. Now we have utilized the differential form of the rate law. We can use the integral rate law expressions also to calculate or to determine the order of a reaction. So this particular method can be discussed in two ways, or we can say that there are two ways in which integrated rate law expressions can be employed, right? How can you use? You know that what is the integrated rate law expression. Let's say for first order reaction, A upon A minus x, log of A upon A minus x equal to kT. Now this particular rate law expression, integrated rate law expression, I can use it in two ways. One is analytical way, right? Another is graphical method. In analytical method, what do? For a given reaction, I assume the order. Let's say I do not know in the beginning that what is the order of this reaction. So what do? I assume that, let's say, the order of the reaction which I am carrying out is first order, right? And then using the integrated rate law expression for first order, this is first order, right? And I carry out the calculations of rate constant. So I carry out the reaction and for calculation. So carry out the reactions means I will observe the concentration of the reactant at different times, calculate A minus x and T. I know all these values, all these constants, and then this K, rate constant, can be calculated at all the times, right? The constancy, if I get the value of K constant, right, it means the order which I have assumed for a given reaction is correct. Alternatively, if I get all these values which are haphazardly placed, right, they are all different values, then what will happen? I will have to assume a different order. So let me tell you one thing, that this method is completely hit and trial method. So I have to assume the order. If for that same order K comes out to be constant, it means the assumed order is correct, otherwise I will have to assume a different order, right? In the same manner, you know that this is the extension of this analytical method only, graphical method. So what can I do? I already explained that the plot between log of A upon A minus x and T, it is going to be a straight line, right, which passes through origin, right. So again what I do? I assume the order of this reaction. I then calculate the initial concentration of the reactant at any point of time, and then I make a table wherein the concentration along with time are mentioned, and then I plot a graph between log of A upon A minus x versus time. And if I get the correct trend of the graph, it means if I assume the order to be 1, that means my reaction follows first order kinetics, the graph between log of A upon A minus x versus T should come out to be a straight line. So if I get the straight line, that means the assumed order is correct. The next method is the isolation method. This is a very common technique. Usually we do follow this technique in the laboratory in order to find out the order of a given reaction. So what happens basically, the kinetics of a reaction here. So suppose I have the rate of a reaction which is related to the concentration of the two reactants A and B, right. So what do? I carry out this experiment by keeping one of these reactants in excess. So what will I do? I will take reactant B in such a large excess that its concentration will not affect the rate of a reaction, right. So its concentration is not going. So practically what will happen, that my rate will only depend upon the concentration of A. It will not depend upon the concentration of B. One such example is the example of hydrolysis of ethyl acetate, water, and then we get ethyl alcohol and acetic acid as a result. So here water is taken in excess. If I take water in excess, my rate of this reaction will not depend upon water at all. It will only depend upon the concentration of the ethyl acetate. So in order to determine the order with respect to A, I keep B in excess, and then in the next set of experiment, what will I do? I will change this order. So in the first step, I will find out the order with respect to A, and then in the next go, I will keep A in excess. And then my rate of reaction would not depend upon the concentration of A, but will only depend upon the concentration of B, and therefore I can find out that how it depends upon the concentration of B, right? We may change their concentrations also, like suppose in like the alternative method to this is that also that we may double the concentration of A, keeping the concentration of B constant. Then also I will come to know that how my rate varies with the concentration of B. In the next set of experiment, what will I do? I keep the A constant, means the concentration of A constant, and double the concentration of B, and then see that what kind of dependence will rate have on the concentration of B. Whether my rate also doubles on doubling the concentration of B, or it remains same, right? So this is the way how I can make use of the isolation method. And then the last method is half-life method. We've understood in the previous lecture that what do we mean by half-life. So half-life, the general formula for half-life, right? Means for any reaction which is of nth order, right? Half-life for an nth order reaction is related to the initial concentration like this. T half is inversely proportional to the initial concentration raised to power n minus 1. So what I can do is I can take these observations, note down these observations with two different initial concentration. First, let's say I start with maybe 1 gram of the reactant. In the next set of experiment, let's say I start with the 2 grams of the reactants. So it means that in the two successive experiments, I have changed the initial concentration, and note down that how much time it requires to come to the half of the initial concentration, and then manipulating this equation. This is simple mathematical manipulation, that for first and second, so it has an inverse relationship. So therefore T half for first set divided by T half for second set, it will have A2 in the numerator and A1 in the denominator. And again, what can you do? What is my unknown? What is my aim? Is to determine the order. N is the order of reaction. So I can simply rearrange these two. I can take log on both sides, and then I can find out that what my N will be. So this was all about the different methods, experimental methods to find out the order of a reaction, right? We mentioned in the beginning only that order is an experimental quantity. Just by looking at the reaction, we cannot say that what order will this reaction follow. So these are the methods by which you can find out the order of a reaction. So in the next part of this lecture, I will be discussing about the various theories of reaction kinetics.
Hi, welcome to Chand Academy. This is Dr. Garima Kaba and I am coming for you to explaining about all the coordination chemistry topic, which will be including about transition elements, lanthanide actinides, about CFT, LFT. So please like, share and comment on these videos and do not forget to press the bell icon so that you can get all the notification. So please stay in touch. Thank you.
Welcome back to Chand Academy. So in this part of the lecture, we are going to discuss about various theories of reaction kinetics. The earliest theory of reaction kinetics was proposed by Arrhenius. Arrhenius basically related the rate of a reaction with temperature. He said that how the rate of a reaction varies with temperature. So this equation basically helps us to explain the increase in the rate of reaction on increasing the temperature, right? So Arrhenius took the idea or imbibed the idea from Maxwell-Boltzmann distribution curves for molecular energies. So he said what happens, what actually leads to the increase in rate of the reaction upon increasing the temperature, what exactly happens. So he said that what happens that at an elevated temperature, molecules are moving with higher kinetic energies. So we have already seen that in the gaseous state also, that at high temperature molecules are moving with higher kinetic energies. Now when they are moving with higher kinetic energies, they are able to cross that threshold barrier. Now let me explain you the two graphs. First is the the molecular energies versus temperature. So this is the kind of distribution which these molecules favor. Let's say at temperature T1. Now T2 greater than T1, I take another temperature which is higher than this temperature. So what happens? We have seen that this entire curve gets flattened towards right direction, and what happens that, let's say if I want to calculate the number of molecules which are having kinetic energies between this and this are represented by this area. Now if I increase the temperature, more number of molecules are having higher kinetic energy. So one thing is clear from here, from this graph, that the number of molecules moving with higher velocities increases at higher temperature. Now another graph which tells you that with these increased energies, the molecules are able to cross, more molecules rather are able to cross the threshold barrier. So let us understand that what is threshold barrier. So this is energy and this is your reaction coordinate. This is where in my energy level profile diagram my reactant lies. I represent my reactant with R, product with P, and it follows this kind of energy profile diagram, right? Now it is at this energy, so reaction is feasible, therefore product is having lesser energy. This is the energy which is called activation barrier. What do we call it? We call it activation barrier. We all know that for doing certain work we need some amount of energy. So in the same manner, molecules also need energy in order to undergo chemical reaction. Now this is the activation barrier. So in order to undergo chemical reaction, molecules have to have this much of energy so that they can cross this barrier and form product, right? The difference between the activation barrier and reactant, energy of the reactant, is called threshold energy, right? Now what happens at higher temperature, that more and more number of molecules are having energies higher than threshold energy, right? So what happens, that earlier maybe 20% molecules were able to cross this barrier. Now at a higher temperature, let's say 50% molecules are able to cross this barrier. More molecules with more energies, and therefore they undergo this chemical reaction and form the products. So it is because of this reason that at higher temperature rate of reaction also increases, because we know that only those molecules which cross this barrier are, they can be called as undergoing effective collisions. Effective collisions means the collisions which can lead to the formation of the product. So at an elevated temperature, more number of effective collisions are happening. And this kind of dependence of rate constant on the temperature for a reaction is given by Arrhenius. This is called Arrhenius equation. This is your rate constant. A is called pre-exponential factor, and this is your activation barrier and temperature. So K here we can see that it depends. So we have T in the denominator over here, but we have a negative sign too. So therefore, taking the log of this equation also, it is quite clear that what kind of dependence K has on temperature? K increases with increase in temperature. Now very briefly, I would also like to explain here the effect of catalyst on the rate of reaction. We've already understood, we've already discussed about the effect of catalyst, that catalyst enhances the rate of reaction by providing a way that it enhances the rate of reaction, but it will not undergo any chemical change on its own. But then the question comes that how does a catalyst helps in increasing the rate of reaction? So let us have again look at this diagram. This is your reaction coordinate and energy. So let's say my reactant here and product is here, and it is following this pathway. So this is my reaction pathway, and this is my EA1, activation barrier in the absence of catalyst. So what a catalyst does? So catalyst provides an alternative path. It does not lower. The misconception sometimes is there in students' mind that catalyst lowers the activation barrier, but no, catalyst does not lower the activation barrier. It provides an alternative way. It provides an alternative reaction path with lower activation energy, right? So it provides an alternative path. Now see, even at normal temperature, even without raising the temperature, what will happen? Since the barrier is low, more and more number of molecules will be able to cross this barrier, and hence the rate of reaction increases. There's another theory, like there are two famous theories for reaction kinetics, which are collision theory and activated complex theory. The collision theory is the earliest theory which was given by Arrhenius and Van 't Hoff, and he said it is indicated from the name itself that in order to undergo a chemical reaction, molecules will have to come close to each other and undergo collision. So it says that molecules collide with each other, and the effective collisions will lead to the formation of the product, right? So the collision theory basically explains that what are the factors upon which the rate of a reaction depends upon. Now this collision which is happening, right, for the sake of simplicity we are considering here bimolecular collision, means only two molecules, they are coming close to each other, undergoing collision, and to be simplify it further, we are taking into consideration gaseous molecules. As I mentioned in one of my lectures, that gaseous state is the most studied state of the matter. So for gases we have many expressions, therefore we are using this particular model by taking the example of gaseous molecule. So gaseous bimolecular collision, right? So out of all the collisions, now collision theory says that in order to have product, collisions are happening. So we all know that these gaseous molecules are randomly moving, right? They are moving with different velocities. So while moving, they are colliding with each other. Now so many collisions are happening at a point of time, and not all these collisions are effective. So what are those effective collisions? Only the ones which are able to cross the threshold barrier, right? So this is the, so collision theory basically gave the quantitative expression for the number of collision. So if I assume that let's say I have n number of molecules in a gas, then my number of collision taking place in unit time, in unit volume, will be given by this expression 1, which is called collision number also. This is the same expression, but if we have different type of molecules. So we have this expression again, which gives us the number of collisions taking place per unit time, per unit volume, and here the term mu is nothing but, see, we all are familiar with these terms, only mu is different. Na is number of molecules of type A, of type B, D is collision diameter, 8 pi kt upon m, usually we write that is your average velocity, but here we are taking mu instead of m. So what is this mu? If we have different types of molecules, we would like to define here the effective mass. We call it reduced mass also, which is given by Ma Mb upon Ma upon Mb. Inserting this, we would be having this final expression, which gives us correctly the number of collisions which happens at a particular temperature in unit volume per unit time. But using this expression, when the number of collisions were calculated, let's say for the reaction between hydrogen and iodine, H2 and I2 would give you 2HI. So the number of collisions for this particular reactions were calculated, and it was found that the number of collisions which were predicted by collision theory were much more than the number of collisions which are actually taking place. So here I would just like to mention or highlight one of the limitations of collision theory, right? The limitation was that it considered or it assumed the molecules to be hard spheres, right? Rigid spheres, right? So if we take the spherical model for the molecules, they we might be ignoring the orientation factor, because sphere is sphere, it is similar from all sides, right? So that means in a way we are saying that all collisions will be affecting, but collision theory suggested that only those collisions which are effective would lead to the product formation, and effective collisions are the ones which cross the activation barrier as well as are happening in the correct orientation. So if the orientation in which the molecule approach each other is not correct, then they would not lead to an effective collision. And if we consider the spherical model for these gaseous molecules, this model ignores the orientation of colliding molecules. So it means, in other ways, it says that in whichever orientation they come close to each other, reaction would always occur, right? So which is not true. So this is one limitation on the basis of which we were getting the kind of different results as per collision theory and experimentally. So this reason explains why we were getting lesser rate of reaction experimentally compared to what it has been predicted by collision theory of gases. So considering the limitations of the collision theory, a little more advanced theory which is called activated complex theory, and this has an alternative name called transition state theory, was also given, right. So this theory was given by Eyring and its fellow members, and what he suggested that in order to undergo a chemical reaction, let's say I have A2 and B2 as my reactants, and as a result we have the formation of AB as a product, right. So this product formations occurs via the formation of an activated complex. So again we can draw this energy level diagram, energy profile for a reaction, and it says that reactant product, in between the reactant and product what will happen. So this is, let's say, my A2 and B2, and this is AB getting formed. In between this, it will undergo the formation of an activated complex, which is what? So what happens if it has to form AB? The bond between A and A has to break, and similarly the bond between B and B also has to break. So as a result, what will happen? The bond between A and B gets formed. So B and B, you see here, the bond is getting elongated. Here also it is getting elongated. So this bond is getting weakened, and at the same time the bond between A and B is getting formed. So this kind of structure which is formed in between the reactant and product is called an activated complex. It is higher in energy, as we can see from the energy level diagram also. So we denote it by A2, B2 and here hash, right. So this is your activated complex. So activated complex theory suggested that the product gets formed by the formation of this transition state, right. And then slowly, so this is higher in energy. Definitely something which is higher in energy is going to get stabilized by releasing its extra energy. And very briefly I would like to mention about the characteristics of this activated complex. So activated complex is always in equilibrium with the reactant, right, and which then decompose into product, and it will have one vibrational degree of freedom lesser, because one vibrational degree of freedom has converted into translational degree of freedom, which has been consumed while the formation of the product, and it is highly unstable. It is lying at the maximum of this curve, so it is clear that it is having higher energy, and the difference between the energy of the activated complex and energy of reactant is known as activation barrier, as we've already understood from the previous slides. So with this we come to the end of this presentation, wherein we have understood the various methods to determine the order of a reaction and the various theories of reaction kinetics. So to read more about this topic, you can refer to the book by S. Chand Publishing. The link to the e-book is given in the description box. Kindly like, share and subscribe, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.